All right, this is 11.4 part 2. So now what we want to do, in part 1 we talked about finding the pH if we knew the constant for the equilibrium constant for the acid or the base. Now we're going to do the reverse. If we know the pH of the solution and we know the concentration of the solution, can we find the equilibrium constant? So we're going to start with a generic one. We'll call it our weak acid HA. Why does it need to be a weak acid? Well, those are the ones that are in equilibrium. We know our strong acids and strong bases have only single-sided arrows. So we have a weak acid. We know its concentration and we know its pH. So as always, we're going to start with a Rice table. Since this is a generic weak acid, our formula looks like the weak acid HA, which is aqueous, in equilibrium with the acidic hydrogen ion, also aqueous, and the anion, aqueous. And we're going to fill in what we know into our chart. Our initial concentration is 0.300 molar. We have no hydrogen ion yet and no anion yet. For our pH, we're going to use that to find the change. So if we recall that the hydrogen ion concentration is equal to 10 raised to the negative pH, or what we call the antilog, we can take the antilog of our pH of 2, and we get 0.010. This is the concentration of our hydrogen, which goes right there. So we can write that in, 0.010. And so that means that if we, at equilibrium, have 0.010 molar of hydrogen, we gained 0.010. Hydrogen has a coefficient of 1. Our anion has a coefficient of 1. So they're in a 1-to-1 ratio. So we also gained 0.010 here, which is in a 1-to-1 ratio with the acid HA, which means we lost 0.010 here. And that means our equilibrium concentrations are 0.3 minus 0.01, which is 0.290, and 0 plus 0.010. And so once we've filled in our Rice table, our goal is to get the Ka. Our Ka expression is the products over the reactants raised to their coefficients. And so we can actually plug in all of these concentrations from our equilibrium line. So we have 0.01 times 0.01 over 0.290, and plug that into our calculator, and we get 3.4 times 10 to the negative 4th. So what we've done here is used what we know about pH and our negative logs and the concentration to work backwards to finding out the equilibrium concentration, or excuse me, the equilibrium constant. So let's do another example. As always, I would recommend that you pause the video here, try this yourself to make sure that you can solve for it, and then come back to the video to check your answer. So going over this, we have a 0.15 molar solution of a weak base, and we know its pH. So we're going to start with a Rice table. Writing out my generic base, we have XOH, which would be aqueous, in equilibrium with its products, which are the cation X and the anion hydroxide, which is what makes it a base. Start with what we know. Our initial concentration of the base was 0.15 molar. And then we can use our pH to find the concentration of hydroxide. Now, pH is the concentration of hydrogen. We need hydroxide, so we're going to do 14 minus the pH to get the POH. So that's 14 minus 10.5 equals 3.5. once we know the POH, then the hydroxide ion concentration is equal to the the inverse log, or anti-log, of the POH. So that's 10 to the negative POH, which is 3.5. And we can solve for that and get 3.2 times 10 to the negative fourth. This number represents the concentration of hydroxide at equilibrium, so we can plug that in here, 3.2 times 10 to the negative fourth. Forgot to write in, these were 0 initially. That means we gained 3.2 times 10 to the negative fourth. In a 1-to-1 ratio with the x, we gained 3.2 times 10 to the negative fourth. And in a 1-to-1 ratio with the base, we lost 3.2 times 10 to the negative fourth. Going through, what is 0.15 minus 3.2 times 10 to the negative fourth, the 2 sig figs? It's still 0.15. And here you can see why we were okay in making that assumption before that x is negligible in part 1, because really something this small doesn't impact our overall concentration. So it is still 0.15. We're finding our base equilibrium constant. So that's going to be the concentration of the products over the concentration of the reactants. I'm going to plug in what we know, 3.2 times 10 to the negative fourth times 3.2 times 10 to the negative fourth divided by 0.15, and we find that the equilibrium constant for this particular reaction is 6.8 times 10 to the negative 7th. Remember that equilibrium constants have no units. They're unit-free numbers, whereas if we're talking about equilibrium concentrations, they have the unit of molar. All right, that was part 2 of 11.4. Good luck and happy chemistry.